It's fine. Oh, okay, but the point, like that, like. And it's like, it's cash or whatever. And then.
Okay, page 26. This is the last topic before we begin our quiz review. So I think we're going to be able to have some time at the after I get through this lesson. So you guys picked up kind of like a pre-review sheet. It doesn't have everything on it, just has some of the initial topics that we've gone over this past week. So, but we'll begin our full quiz review tomorrow. Yeah, I think we're gonna have some time to begin a review. So I printed out a pre-review sheet. Okay, so today's topic is arc length of curve and distance traveled. So we're going to be finding the distance along a curve or the length of a curve. A lot of it is coming from the idea of distance traveled. So we're going to take distance formula and adapt it for a curved graph. So the idea behind finding arc lengths is very similar to the way that we find area using calculus. We're going to divide the curve into a large quantity of small segments, find their lengths, and then add them up. So if you recall, distance formula looks like this. Distance between two points along a straight line segment. Okay, we can approximate the length of a graph of a function f by using n line segments whose endpoints are partitioning between a and b. Think of it this way: a equals x of 0, b equals x of n. So the idea is that we can take any curve, and if we zoom in on the graph far enough, it'll begin to resemble a very short straight line segment. So the idea is that if we add up infinitely thin straight line segments, we're going to be able to achieve the length of this curve if we add up all those regions up. Okay. Yeah, so just want to show a couple of instances where if we take a line segment between two endpoints, if we continue to break it up into smaller and smaller segments, it's going to begin to resemble the actual shape of the curve. And if we keep making the line segments shorter and shorter, it'll adapt to every change in the graph, and we can eventually find the exact length of the curve. So the reason that I also want to show this distance formula is that your arc length formula will have a resemblance to this distance formula between two line segments. So if a function y equals f of x represents a smooth continuous curve on the closed interval, then the arc length of the curve between a and b is given by this formula. Integral from a to b, square root of 1 plus f prime of x, quantity squared, dx. So we're using f prime in the function or in the formula because of the connection to the infinite numbers of tangent line segments that we're going to be adding together. So if you want to see that there's a resemblance between distance formula algebraically, and then this essentially is distance along a curve involving calculus. So there's kind of like three ways that we need to be able to use or apply this formula. The first way is sometimes the problem is just asking for you to just set up the problem. And that can be the answer. Or set up the integral. Another way that a problem is asking you may be where you set up and then you simply just plug in the calculator to find that distance. And then the third potential problem is where you set up and then you solve manually by hand. So just using whatever integral rules, whether it's use substitution or power rule, option 3 tends to have to be an easier problem in order for us to be able to work it out by hand. So just be aware that, these are the 3 types of problems that may be involved, just depending on how the problem is set up. But largely, we're just jumping directly into the formula, finding the derivative, plugging into the formula, and then solving. So it says number 1 says find the arc length of the curve from x equals 1 to x equals 4. So the bounds are given. So that's our a value. That's our b value. We have to build f prime, and once we have f prime, then we're ready to put into our formula. So say L is equal to arc length. Okay, so this one we're going to solve by hand. So let's find y prime, and then y prime will take the role of f prime. So this one we can go through chain rule, right? For derivatives. Outside times inside derivative. So we'll take the outside derivative first. Bring down the exponent. Subtract 1 from the exponent. Times the inside derivative. So we're doing outside derivative for the parentheses. And then inside derivative. Okay, let's do some cleanup here. So 3 over 48. 2 times, sorry, the 2's cancel out. So just 3 over 12 or 1/4. Or we can say x over 4. Okay, so y prime basically is the same thing as f prime. So we can just put into our arc length formula. So we're going to go from 1 to 4, square root of 1 plus then f prime squared. F prime is just going to be this whole expression here. And x squared plus 8 to the 1/2, that's really the same thing as square root of x squared plus 8 dx. All right, this looks messy to solve by hand, but I think a lot of things will clean up nicely once we undo or resolve the square root, the square and square root. Oh, I do want to point out something is that we cannot simplify this and make it just 1 plus f prime and just cancel the square root and the square because there's a plus in here. So we do have to kind of leave it in this form. But here we're able to resolve the square and the square root because this is a square root inside an exponent. There's nothing being added between the terms here. So so we're just going to square everything we see inside that bracket. So everything gets squared inside the bracket here. So x gets squared, the 4 gets squared, the square root gets squared, and the square root and square will cancel out. So I get x squared over 16, parentheses, x squared plus 8. If we go through manipulation here, we can factor out a 1/16 out of both these terms. And then we're left with 16 plus x squared plus 8. I'll just show you where this is going to lead here. So distribute that through, we get x to the 4th plus 8x squared plus 16. This actually factors. So we get x squared plus 4 and x squared plus 4. Now, the square root of 1/16 we can pull out outside the square root. So we know that square root of 1/16 is the same thing as a 1/4 in the front. So we can really take out a 1/4. And this is where we can do some cleanup because there's x squared plus 4 quantity squared. Now these can cancel out because there's no addition, subtraction that's separating the terms outside the parentheses. So this is a clean canceling out. Now this becomes a lot easier to evaluate. And then we plug in our upper and lower bound. And that's going to come out to be 33 over 4 after we go through all the numerical plugging in. Okay, most of the problems, though, should be a little bit cleaner in terms of it's either going to be just plugging into the formula, plugging into the calculator, or or working out by hand. So just want to show what an example of working out by hand is. But again, you have your calculator, so you can use your calculator to confirm your answer, even if I'm asking for your steps. Okay, next page. Often the problem will only ask you that you set up the integral, or you may have to use a calculator to actually plug in and find the arc length. So number 2 is to set up an integral that represents the length of a curve, y equals sine of x, between 0 and pi, and use calculator to find the value. So here we can just put directly into our formula here. A and b, 0 and pi. Square root of 1 plus f prime. What's f prime or what's y prime going to be? Sine is just cosine, yep. So we can just make it 1 plus cosine squared dx. Okay, so there's the setup. And then the calculator, we can just plug into the calculator. So math 9 from 0 to pi, square root of 1 plus, and then put a bracket around cosine square it. The next part is just a proof that shows how algebraically we can get from that arc length formula to the from the distance formula to the arc length formula. But let's go ahead and try practice problem number 1. And this one is just set up as well. Okay, very similar to the number 2 above. Right, next page. Okay, number 2. The length of a curve is given by the definite integral. If the point 1,6 is on the curve, which of the following could be the equation of this curve? So we're kind of working backwards here. We have information about f prime, and we're just trying to work backwards to figure out, what's the f of x that is causing this to be 4x squared. So we're having to work backwards from our arc length formula. So let me write the arc length formula here so we can just kind of match up the parts with this problem. So it's basically asking what is f of x for this problem. So we know that if we line things up here, we know that 4x squared is related to that f prime. So we know that f prime of x squared is related to that 4x squared. Right. And if we continue to undo this process here, if I want to find f prime would just be the square root, which would just be 2x. And if f prime is 2x, then we can find f of x by taking the antiderivative. Okay, what's the integral of 2x? Plus what? C. And they give us an ordered pair to help us find that C value. So 1 goes in for x, 6 in for y. Then solve for f of x. right, next up, suppose uppercase g of x is the integral from 0 to x of root sine of t. What is the length of the arc along the curve for the region for the interval from 0 to pi over 7? Okay, so we just have to find g prime and put it into the formula. Well, if g of x is the integral, and g prime is just going to be what? Yeah, second theorem. So second theorem, if we take the derivative of this will just turn into what? Yeah, square root sine of x. So remember, we keep everything intact. We just remove the integral and then plug in the starting variable with the x. So yeah, so we keep everything the same. We're just dropping the integral. Okay, so now we just put into our arc length formula and then make the calculator find. Now, because there's a square root and a square, I think this will just clean up to be just sine of x. So just square root of 1 plus sine of x. Okay, so practice putting that in the calculator, see what you get. Make sure you're in radian mode. Okay, for number 4, no calculator. We're going to see if we can work through. It's basically helping us break down each of the parts of the arc length formula. So first, we're going to find the derivative. So g of x equals root 3x. Oh, it says g of x is it says f is the integral of g. So we know that f is the integral of g. So therefore, f prime is just going to be root 3x. Okay, find an expression for the arc length from A to B. So we don't have a replacement for A and B. We're just going to hold on to those letters provided. Oh, we're just setting it up and then they're giving us the actual A and B values for part C. Which can clean up because of the square root and square. If A is 0 and B is 8, find the arc length of f from A to B. So I think this is easy enough where we can work it out by hand. Use substitution, should be able to get us there. Okay, so u value, what's our u value here? X is 1 plus 3x. Yeah, it should end up just be a pretty clean u substitution problem. We do have a leftover coefficient to keep track of. We keep track of the leftover coefficient. We know that's just power rule for u to the 1/2. We apply power rule. Oops, left off that 1/3 there. Okay, so now we can plug in our upper and lower bound. One plus 24 is 25. That 2 there indicates square root. So square root of 25 is 5. All right, number 5. Consider the region bounded by the graph of y equals x squared minus 4 and y equals 5. So if you think about y equals x squared minus 4, the graph looks something like this. And then y equals 5. Write an expression involving one or more integrals that could be used to find the perimeter of this region. So we want to figure out what is the length of the curve and this line added together. Okay. If we can set these equal to each other, we can figure out where these endpoints are. So we know that this has an x value of 3, -3, 2, 3. So we're going to use says find the perimeter. This we can figure out, right? That's just a horizontal line. We don't need a distance formula or arc length formula to figure that distance out. What's the distance here? 6, yeah. What we do need help is with the curve, right? If we want to find the distance of this curve, we're going to use arc length formula. But whatever we get from our integral, we can just add it to 6, right? So let's do arc length formula for the x squared minus 4. So we know that the x squared minus 4 is related to this curve. So we're just going to put information into that formula. So we're going to go from -3 to 3 along this parabola. Root 1 plus f prime squared. What's f prime going to be? 2x. Okay, so we make 2x squared. So the perimeter is just going to be this plus 6. So we can make the calculator find this portion for us. Okay, the next page is more of the same, just applying the formula in these various ways. So I like to shift over to our review worksheet. Now, I just pulled this from practice from the textbook. So this is practice problems. Your quiz is not going to be multiple choice format. I just pulled this just for us to kind of begin our initial review over the topics that we've covered since last Tuesday. All right, so number one, we want to find the depth integral of x e to negative x dx. If we look at this problem and think about u substitution, it's not going to quite fit, right? There's no u value that will allow this to clean up to be something that we can identify as a rule. So we have to rely on integration by parts, either tab method or the original integration by parts. Let's do tab method for this because we need to do something else for number 2. So again, you have 2 options here. But let's just practice tab method for this since we can do tab method. Again, we can only do tab method if you're pairing 2 different types of functions being multiplied and there's no logs involved. Okay, if there's no logs involved, then you can always let your algebraic or your polynomial expression be your f. Right, so your f is going to be your x, and your g prime will be that exponential portion. Again, we could do it the other way as well. I just picked tab for this because we have to do something else for number 2. Just want us to see the different varieties. All right, so on the f side, we keep finding the derivative until we reach 0. On the g prime side, we keep taking the antiderivative until we reach the same number of times as the left column. So what's the integral of e to the negative x? It's a little bit of u substitution. Your u value is negative x. It's going to produce a negative 1. We know e to the u is just e to the u, but there's a negative that's going to tag along. And then we take the integral again. We're going to get what? E to negative x. Yeah, another u substitution. Another negative 1 will pop up. Another negative 1. So this will cancel out as well. Okay, so remember with tab method, the way that the 2 columns are going to line up is a diagonal. So start at the upper left corner, and then you're going to multiply by the diagonal below. And then you're going to alternate signs, starting with a positive times positive 1 times negative 1 times positive. Okay, so now that we have our indefinite, our antiderivative, we can plug in our upper and lower bound. Careful with zero. I think sometimes when we see zero, we just assume that everything goes away. It does happen a lot of times, but just make sure that you're actually checking to see what's happening. If I plug zero into the first expression, it does zero out, but zero into the second expression doesn't quite zero out because the zero is in the exponents. So e to the zero is still going to be a what? It's going to be a 1, yeah. So these are like terms here. I can make this -3 e to the -2 minus negative. For number 2, integral of 3x squared plus 2 times sine x. We have u substitution is not going to quite allow this to clean up to be something that that we can recognize. So maybe you're thinking, okay, this we could do tab method. However, if you look at your answer choices doesn't quite finish the problem. There's still integral left over. So based on the answer choices, let's apply integration by parts of the original formula, since the answer is only going to work the problem halfway. So here's a reminder of the formula. Integral of fg prime is equal to fg minus the integral of f prime g. So the first thing is identifying your f and g prime. You're choosing between 3x squared plus 2 and sine of x. Again, there's no logs involved, so our f can always be the algebraic. And the other is going to be your g prime. On the f side, we'll find f prime. On the g prime side, we'll find g. Okay, what's f prime going to be? X. Antiderivative of sine is okay, so we just put it into our formula here. So fg minus integral of f prime g. And we should be able to kind of pause here and see that our answer choices is already showing here. So I think that's going to be best fit with answer choice B. The 2 negatives can cancel out. We can pull the 6 out in front to make it match. Okay, for number 3, if we see a rational expression, we should always consider u substitution first. However, our u value is not going to quite, the denominator is not going to quite match up nicely with that numerator. But we see that the denominator is factorable. The denominator has a higher power. We're going to rely on potentially partial fraction to break this up into easier portions. So let me get this expression factored out in the denominator. Multiplies to be 2, adds up to be 3. And then we can begin breaking into our separate parts. You can multiply everything through by the denominator to clear the fraction, and then pick out strategically pick out your x values. I like to just go through this method of cover-up method where I find one critical point and plug into the original expression, but I make sure I cover up the part that that's involved. So I want to cover up the x plus 2, replace all the negative, all the remaining x's with negative 2. So negative 2 in for x, I get negative 2 minus negative 2 times 2, which is negative 4 minus 1 is negative 5. And then in my denominator, negative 2 plus 1 is negative 1. So we know a is just equal to 5. And then for b, you cover up the x plus 1 and plug negative 1 into the remaining x's in the original problem. So negative 2 minus 1 is negative 3. And then negative 1 plus 2 is 1. So b is negative 3. So when you go through partial fractions, just remember that we haven't solved the problem yet. We just made the integral a little bit easier to resolve. So we just have to go through a little bit of u substitution and log integral to find our answer. So natural log for both of these. And we still have to evaluate our bounds, so plug in our upper and lower bound. Natural log of 1 is just going to turn into 0. These are like terms. So negative 3 and negative 5 is negative 8. Number 4 is also partial fraction, but there's something else going on. Let me set up partial fraction first and see if we can spot what else that we have to be aware of. So we see the denominator can be factored. Okay, so there's a factor at negative 6. Plug negative 6 in for all the x's, I get negative 4 over negative 8. Plus 2. Did you guys get 1/2 for A? Yeah. Okay. One half for B as well. Okay. So we have our A and B values. That's good to go. However, there's bounds involved, but is there an issue that you see? There's a vertical asymptote at 2, and there's a boundary at 2 as well. So that issue just indicates that we have to involve improper integrals. We have to do limit as B approaches 2, approaching that asymptote, but we know that we can't quite hit that asymptote because not at least the original state here, because 2 doesn't exist at that point. So there's an improper integral because the upper bound is at x equals 2. So let's just set up this problem here. So natural log for both, 1/2 is going to stick around. This is going to be limit as b approaches. Now we're going from 0 to 2, and we're approaching that asymptote from the left side of 2. So it'll be approaching 2 from the left side of 2. So if we can show that one of these is going to infinity, then the whole thing will just be diverging. So imagine plugging values close to 2 and then continuing getting closer and closer. So if my b value starts off at 1.9, then what's going to happen if I use 1.99? And what's going to happen if I keep plugging in a value even closer towards 2? So imagine it's not going to impact this one here. That's going to be fine. That's going to be just 2 plus 6. But if I plug in 1.9 in for b, 1.9 minus 2, the absolute value is going to be 0.1. This will become 0.001, 0.0001. If we get closer and closer towards 0, that natural log is going to go to negative infinity. So if anything diverges, the whole thing diverges. Okay, your homework is just to finish the second page here. Pages, the problems, page 2, 5 through 7. I'll check this for homework tomorrow. I'll send out a reminder. I'll send out a link where you can check your answers as well.
Yeah, my first year was
Thank you. Good. Thank you.